Continuing on with section 15.9, I got cut off to answer a phone call, unfortunately. Sorry about that. So let's get back to where we were. All right, so we were here trying to show that we did have a linear transformation, that these 1, 2, 3, 4 lines become these 4 lines, although they're no longer horizontal or vertical. So for L1, V is 0. So V is 0, I plug in 0 there and 0 there. X is 2u, y equals u. A little bit of algebra tells me that x is 2y or y equals 1/2 x. All right, so L1 here becomes L1 here, y equals 1/2 x, which is linear. And that makes sense if you're going from 0, 0 to 6, 3. Do the same thing for all the others. L2, u equals 3. So I plug in u equals 3 right there and right there. I get x is 6 plus 3v and y is 3 minus v. A little bit of algebra, v is 3 minus y. Plug that in here. X is 6 plus 3 times 3 minus y. You could make that look like y equals mx plus b, but basically it's also linear, okay, which means I can go in a straight line from 6, 3 to 12, 1. And all the others can be shown to be linear also. L3, v equals 2. So plug in v equals 2 there, v equals 2 there. That gives me x equals 2u plus 6, y equals u minus 2, u equals 2 plus y. Plug that in over here, x equals 2 parentheses 2 plus y plus 6. That is also linear. You can make it look like y equals mx plus b. So this 3 marks here, 3 lines there, becomes this linear transformation. You're going in a straight line from 12, 1 to 6, negative 2. And finally, L4 is pretty easy, u equals 0. So plug in u equals 0 there, u equals 0 is there. So x is 3v, y is negative v. That means v is negative y, or x is negative 3y, and that's also linear. All right, so the quadrilateral determined by 0, 0, 6, 3, 12, 1, and 6, negative 2 is what the transformation becomes. So it used to be here, it now ends up like this. So remember in Calc 1 and 2, right? Your interval was from 3 to 10, and then it got changed from 7 to 45 or something like that. Now, multivariable, this rectangle gets transformed to this quadrilateral. Okay. All right, 9, you have the point 0, 0, 1, 1, and 0, 1, x equals u squared, y equals v under this transformation. Okay, so 0, 0, 1, 1, 0, 1, this is u equals v, v equals 1, u equals 0. I called it L1, L2, and L3. Now, plugging in seems fairly benign. You plug in 0, 0 for u and v, that gives me 0, 0, and x and y. 1, 1 gives me 1, 1, and 0, 1 gives me 0, 1. So this, what's the big deal? The 3 points stay the same. The 3 points do stay the same, but let's actually see what happens. Doesn't mean I have the exact same shape. L1, u equals v. So if u equals v, I have x equals v squared, y equals v, which means x equals y squared, or y equals radical x. So that is parabolic. Okay. So that means even though you're still going from 0, 0 to 1, 1, I'm no longer going along a straight line. I'm going along y equals radical x, square root function. L2, v equals 1. If v equals 1, then that means since v and y are equal, y equals 1, x is u squared, u going from 0 to 1. Okay, so y equals 1 still looks like that. And L3, u equals 0. So if u equals 0, x equals 0, and that's linear also. Okay, so this is what we end up with. So even though these 3 corner points stay the same, this becomes parabolic, that stays the same, that stays the same. So this triangle region ends up being this region over here. Okay, 13, x squared plus y squared equals 1, x squared plus y squared equals 2. This region here, okay, it looks like it'd be good to switch over to polar coordinates. So x is u cosine v, y is u sine v. Our radius goes from 1 to radical 2, theta goes from 0 to pi over 2. So this region, which is a little bit harder to integrate by means of this transformation, it's much easier because now these are constants and these are constants. Okay, and now for an actual integration problem. 17, double integral of x squared dA along 9x squared plus 4y squared equals 36. X equals 2u, y is 3v. So first I find a Jacobian, which is partial of x with respect to u, 2, partial of x with respect to v, 0, partial of y with respect to u, 0, partial of y with respect to v, 3, 6 minus 0, 6. So that's the multiplication factor that I need. Now notice if I plug in 9 times 2u squared is 4u squared, plus 4 times 3v squared is 9v squared, gives me 36u squared plus 36v squared equals 36. Divide by 36, u squared plus v squared equals 1, unit circle. So the integral becomes double integral of 4u squared, that's x squared, since x is 2u, so 4u squared times the Jacobian 6 dA. 4 times 6 is 24, take that out. So r cosine theta squared, r dr d theta. So that becomes r cubed cosine squared. All right, so that's 24 cosine squared, r to the 4th over 4 from 0 to 1. Plug in 0, you get 0. Plug in 1, you get a half. 1/4. So 24 times 1/4. Integral of cosine squared is 1 plus cosine 2 theta over 2. 24 divided by 4 is 6. Divide that by 2 is 3. Integral is theta plus 1/2 sine 2 theta. Plug in 0, you get 0. Plug in 2 pi, that's 2 pi. Sine of 4 pi is 0. And 0, 0 there. So 3 times 2 pi. Final answer is 6 pi. All right, so the picture is that the ellipse gets transformed to a circle. And we know how to do circles nicely with polar coordinates. Okay, then for problem 15, I messed up the first time. So change that completely here. So double integral of x minus 3y dA, and you're going from 0, 0 to 2, 1 to 1, 2. So it's kind of a clumsy integral, like so, but by means of this transformation, it becomes nicer somehow. So let's see if that's actually the case. All right, this is a linear transformation because this is linear, this linear. Let's see where the points end up. So 0, 0 in x and y. 0, 0. 0 equals 2u plus v. 0 is u plus 2v. You end up with 0, 0. So it stays the same. This one's a little harder because you have to solve 2 equations, 2 unknowns. So 0, 0 stays 0, 0. How about 2, 1? Okay, so x is 2, y is 1. 2 equals 2u plus v. 1 equals u plus 2v. I multiply this equation by 2. 4 equals 4u plus 2v. I subtract up. 3 equals 3u, which means u equals 1. And if u equals 1, plug back in, it gives me v equals 0. So 2, 1 in x and y becomes the point 1, 0 in u and v. Okay, and then the point 1, comma 2, the algebra is pretty much the same. So 1 equals 2u plus v, since that's x. And 2 is 4u, is u plus 2v. Multiply that equation by 2. 2 equals 4u plus 2v, subtract up. 0 equals 3u, u equals 0, v equals 1. So 1, 2 becomes 0, 1. So 0, 0 in x, y stays 0, 0 in u and v. 2, 1 in x and y becomes 1, 0 in u and v. And 1, 2 in x and y becomes 0, 1 in u and v. So that's very conveniently this. And this is a much easier integration than trying to integrate from there. All right, so the Jacobian. So partial of x with respect to u is 2. Partial of x with respect to v is 1. Partial of y with respect to u is 1. Partial of y with respect to v is 2. Jacobian is 4 minus 1, 3. So double integral. Okay, v is going from 0 to 1 minus u. It's functioning like y. And then u is going from 0 to 1 of x minus 3y. So x is 2u minus v minus 3y, u plus 2v, times the Jacobian of 3, dv du. Take out the u, 2u minus 3u is negative u. V minus 6v is negative 5v. Okay, I decided to take out the negative 1. So negative 3, u plus 5v, dv du. So integrate with respect to v, uv plus 5v squared over 2. V goes from 0 to 1 minus u. Plug in 0, you get 0. Plug in 1 minus u. U times 1 minus u plus 5 halves 1 minus u squared du. To make things easier on me, 1 minus u squared is the same as u minus 1 squared. Okay, so I distributed this u minus u squared. So that's going to be u squared over 2, u cubed over 3 plus 5 halves u minus 1 cubed over 3. Okay, the derivative of u minus 1 is 1, so no issues with the chain rule. Okay, if I plug in 0, I do not get 0. That's 0, but that's going to be negative 5, 6. Okay, plug in 1, that's 0. I have 1/2 minus 1/3. So negative 3 times 1/2 minus 1/3 minus a minus 5, 6. Or negative 3 times 3, 6 minus 2, 6 plus 5, 6. And that comes out to be 1. So negative 3 times 1 is negative 3. All right. So that is section 15.9.